All right, let's go ahead and get started with Chemical Reactions podcast number 5, which is on predicting products for double replacement reactions. First thing, I want to go over several rules, sort of familiarize yourself with these rules. As you learned in the last podcast, not every reaction occurs. Sometimes reactants can be mixed and they do not form products. We call that a no reaction. So for double replacement reactions, both of the reactants must be aqueous. Typically, one of the products will be a solid precipitate, but there are exceptions, and I will go over those exceptions in this podcast. Those exceptions involve the formation of a liquid or evolution of a gas. These reactions will also occur. Now, I need you to go find your solubility rules and your solubility table that were given to you in class. You should have those readily available or taped or attached inside your composition notebook. You're going to need those to predict products and see if these reactions actually occur. Okay, and I'm going to show you how to use this, but it's fairly intuitive. You're going to simply find the cation and then follow across to the anion and see if they are present. And Ne means does not exist, Aq means aqueous, solid means precipitate, and of course L for water is liquid. Now, if both products are also aqueous, there is no reaction. That's one way for sure you'll know. You have your reactants, they're both aqueous, your products are aqueous. Well, this simply does not occur. And some of the chemical reasoning behind that is coming up in units that we will get into. But at this point, if the products are aqueous, there's no reaction. So let's get started with our first example here. We have iron 3 chloride. Iron 3 chloride is mixed with ammonium nitrate. Now it's up to you whether you want to use the solubility table or the solubility rules, but I really recommend you use both. And you'll kind of learn a lot of these rules. You'll learn that ammonium, for example, those are all soluble. You'll learn that group 1 salts are soluble. You'll learn that nitrates and acetates, for the most part, are soluble. And then you'll start to pick up on which ones are not soluble. In this case here, I'll do the first one, and then from there I'll let you do them on your own. But we have iron 3 chloride. So I have my iron 3, and I'm going to come over here to chloride and see it's aqueous. And then we have ammonium nitrate, and you can simply be like, oh, all nitrates are soluble. As you see, all these guys are soluble here. Okay. All right. So let's go ahead and move on. Let me get rid of this stuff here. All right. So let's see what we're going to form here. We're going to form iron 3 nitrate. Plus we're going to form ammonium chloride. Ammonium chloride. Now wait a minute, all ammoniums are aqueous. All nitrates are aqueous. This is a no reaction. This reaction will not occur, and I wanted to start off with a no reaction because we're going to get into some pretty complicated reactions toward the end of this podcast. So I'm not even going to look at this any further. This will not occur in nature. So we will move on to example number 2. Silver nitrate is mixed with sodium carbonate. And you can look these up. You should be looking these up. You can refer to the table if you would like. But I'm not going to reference that every time because this podcast would go on a little longer than it needs to. So you need to look these up on your table to confirm what I am writing down here. So these two, does this reaction occur? Will sodium switch places? Remember the couples at the dance? They trade partners. Well, yes, it will. We're going to form sodium nitrate. All nitrates are aqueous. And we're going to form silver carbonate. Now at this point, you may be looking and saying, wait a minute, Mr. Pedersen, silver's on the periodic table. It's a transition metal. Why aren't you specifying the Roman numeral for the charge? Silver is one of those exceptions that I referenced that you would learn throughout the course. Silver 1 is, in nature, that's pretty much the only oxidation state you'll ever find for silver is silver 1. So chemists will often just simply call it silver nitrate as opposed to silver 1 nitrate. All right, so this is going to be your precipitate. Let's go through and balance. 2 silvers, 2 nitrates, 2 sodiums, 2 sodiums, 1 carbonate, 2 nitrates, and we are all set on this one here. Okay, so this reaction does occur. Here's our precipitate that's going to form when we mix these. You remember the little video of the lead 2 iodide, the bright yellow precipitate forming. So this is very similar, and we are able to predict the products using that set of rules at the beginning of the podcast. So example number 3, iron 3 chloride. Iron 3 chloride is mixed with aqueous. So you're being told this is aqueous. Strontium hydroxide. This is a, you don't know this yet, but this is a strong group 2 base, and it will fully dissociate, but I went ahead and I wanted to let you know this is aqueous. Will yield. Okay, so strontium chloride plus iron 3 hydroxide. Okay, so you're going to see here that all of these guys here are going to be solids. This is going to be aqueous. And again, you can look at your solubility rules for that, however you want to do it, but all of the hydroxides in this case here are going to precipitate out. So let's balance. 1, 1. I have 3 hydroxides here. I need to make them 6, so I'll try this, which brings me over to here, which gives me a 2 in front of the iron 3 chloride. That gives me 6 chlorides. So if I come over here and put a coefficient of 3, that's going to balance this chemical equation. Okay. All right, for the next example here, we have lithium sulfite is combined. Sulfite, be careful. Lithium sulfite is combined with calcium nitrate to form. Okay, let's see if this is going to happen. So we're going to have the calcium coming over and combining with the sulfate. They're +2, -2. That works out. Plus, we're going to get lithium nitrate forming. I know that's aqueous. And we can come up here. You are explicitly told that it does form a precipitate. So even though you don't see sulfite on your solubility table, sulfates are insoluble when they combine with calcium. But you know, again, you're being told that there is a precipitate forming. You know it's not lithium nitrate, so it has to be this calcium sulfite. Let's go ahead and balance. Put a 2 here, 2. sulfate, nitrate 2. We have 2, so we're all set with this one as well. All right. Example number 5, potassium carbonate. Potassium carbonate. This is a fun one. Is mixed with hydrochloric acid. That's a strong acid. Strong acid, hydrochloric, are mixed, and they are going to form. Now I'm going to write some things down, and then I'm going to have to explain exactly what's going on. They're going to form this, okay, and then the chlorine is going to combine with the potassium to form potassium chloride. Now, before I even balance this, this is one of those exceptions. This is carbonic acid. And carbonic acid will spontaneously decompose into liquid water and carbon dioxide gas. Let me show you what's going to happen here. It's going to turn into carbon dioxide and liquid water. So ostensibly you look at this and you say, okay, wait a minute, this is no reaction. This is a reaction. Carbonic acid will immediately decompose into a gaseous and liquid product, which means that this will occur. So I'm in a hurry here. Aqueous is going to yield gaseous carbon dioxide plus liquid water. So this reaction will occur. Plus, don't forget our salt, potassium chloride. All right, so now let's go through and balance this here. All righty, 2 potassium, 2 potassium, 2 chlorine, 2 chlorine, 2 hydrogen, 2 hydrogen, 3 oxygen, 1, 2 plus 3 oxygen. This reaction does occur. Gas is evolved, liquid is produced. This double replacement reaction does occur. All right, so here's the bullet that goes through that. Go ahead and jot that down so you remember. These are exceptions that you'll learn as you go. All right, example number 6, acetic acid. Acetic acid is mixed with a strong base. This strong base will completely dissociate into its ions in an aqueous environment. Now you're probably wondering, okay, wait a minute, CHO232, right? CHO232, isn't that the acetate anion? The answer is yes, it is. But I want you to become familiar with how it can be written when we're doing some acid-base chemistry. And if you look, this is the exact same. If I put this hydrogen in front, get rid of that charge, acetic acid, ate is ick, acetate, acetic acid. All right, potassium hydroxide, our base. Now, what do we get when we mix an acid and a base? Salt water. We get salt water. So this time I'll go ahead and write it how you're probably, at this point at least, most familiar with. So we're going to get our salt and we're going to get water. And again, I'm writing H2O a little different. This is commonly done in acid-base chemistry to accentuate the hydroxide and the hydrogen. And we'll learn all about that a little later. Let's go through and see if we're balanced. And we are balanced all the way across here. This reaction does occur because a liquid is produced. So this double replacement reaction does occur. So in closing, now you've learned how to balance chemical reactions, you've learned nomenclature, you've learned multiple exceptions. You've learned how to predict products of single replacement reactions, and now you've learned how to predict products of double displacement reactions. I wonder what will be next. Thank you.